So this is our pleasure to have Dena Firoozi from HEC Montreal. I pronounce it correctly, HEC.
Yes.
She will talk about the exploration and entropy-regularization in LQG Mean Field Games. The screen is yours. Thank you.
And thank you very much. And thank you for the kind invitation. And I'm very pleased to be here virtually. So I'm going to talk about exploration and entropy regularization in LQG Mean Field Game systems. And this is joint work with Sebastian J. Manya. So first, I'm going to talk a little bit about entropy, the concept of entropy and entropy regularization, and I will give some motivations for using entropy regularization. Then I will review entropy regularization in mean field games. After that, I will present our work on entropy regularized LQG MFG systems. Then I will give some ideas on potential applications of this framework, and I will finish my talk with some concluding remarks. So I'm sure that everyone more or less is familiar with the concept of entropy. It is associated with the state of disorder, randomness, or uncertainty in systems. And this concept was first recognized in classical thermodynamics in the 19th century. And nowadays it is used in diverse fields such as statistical physics, statistics, information theory, machine learning, etc. And its applications are far-reaching. It is even used in chemistry. It is used in chemistry and in weather science as well. Entropy regularization has proven a useful tool in different areas. For example, it has been used for developing iterative schemes for solving partial differential equations. Here you see two works listed. The first one constructs a discrete time iterative scheme for approximating the solutions of a class of Fokker-Planck equation. In fact, in this work, the Fokker-Planck equation is viewed as the steepest descent of the negative entropy. And in the second work, a discrete time iterative scheme is developed for approximating the solutions to the HJB equation. Recently, entropy regularization has been used in stochastic control problems and stochastic games, so it has become a popular kind of practice. And in this type of problems, an entropy term is included in the objective function. And this entropy term, in fact, measures the level of randomness which is introduced to the system. And this can be equally interpreted as the level of exploration in the system. For such systems, we are looking for to find the optimal action distribution. So for these systems, the notion of actions are extended to the action distribution. So the space of action is not anymore the deliberative space, but the space of measures. And in contrast to the classical optimal control problem, then usually the control law is a deterministic function of a state. In exploratory stochastic control or entropy regularized stochastic control, the actions are in fact stochastic. So they are sampled with respect to a distribution, and this distribution itself could be stochastic. It can be driven by the sample paths of the states of the system. This one motivation behind this line of research is to provide a theoretical basis for policy search techniques that are used in reinforcement learning, where an agent learns about an unknown environment by interacting with the environment, by trial and error, executing actions and learning from their experiences. And the aim for the agent is to find a suitable action model that maximizes their cumulative reward. And in the process, an RL agent faces the dilemma of exploring new states versus maximizing reward given their current knowledge. So this is called exploration versus exploitation trade-off. And entropy regularization has been used extensively in practice for learning algorithms, and it has been shown that this leads to improved expiration because it encourages expiration, and this helps avoiding the situation where the system gets stuck in a local optimum. And this is especially becomes important for the cases where the reward is sparse, so the agent doesn't receive feedback as much often, and it is more probable that the system gets stuck in an action that has led to the highest reward so far, but that's not the best action. So this is one advantage of using expiration in systems. Another one is that it improves adaptation. So for example, if we consider two robots and they learn to work an area, one of them with expiration, another one without expiration, without entropy regularization. Then if they are put in a maze, for the one which hasn't used entropy regularization or randomization while learning to work, it takes longer to navigate the maze. So this expiration helps to adapt to new situations, and also makes agents more robust with respect to the rare events or unforeseen events, still because they have explored more states in the process of learning when they use entropy maximization. Another motivation for an entropy regularized problem, which is not in the area of learning, is for solving non-convex optimization. So in non-convex optimizations, usually classical methods and gradient descent, they could stuck in a local optimum. And there are some algorithms that use at the core some form of randomization or expiration by randomization to deal with this issue. For example, in the simulated annealing technique, at each iteration, the algorithm randomly samples a solution close to the current one and moves to it according to a probability distribution. And this probability distribution in most of literature is exogenous. So it's like a predefined schedule. In the Langevin algorithm, a series of an independent series of Gaussian noises are added to the classical gradient descent algorithm. And the variance of these noise processes is scaled by a sequence of parameters which are called temperature parameters. So in fact, these temperature parameters determine the level of expiration or the randomization in the problem. So this, the design of this temperature parameter becomes very important. And again, in most cases, this temperature is just a constant or is a function of time. So it has been designed exogenously. So there is a recent work here by Go, Zhu, and Zhu that develops a theoretical framework for designing endogenous temperature schedule, which is driven by the state. And it is in continuous time, and it uses entropy regularization to obtain this schedule, endogenous schedule for the temperature parameter. Okay, so so far I gave some motivations about entropy regularizations, how it can help to solve problems in different fields like numerical methods, learning algorithms, and in non-convex optimization problems. So in this work, what I'm going to present is to formulate the exploratory version of linear quadratic Gaussian mean field games. So for short, I will refer to this as LQG, and by LQG, I mean that the agents are following linear dynamics and they have quadratic cost functions. And in this, we consider the case where there is an entropy regularization And we obtain the solutions for the exploratory version of the problem and compare them with the classical solutions. We have chosen LQG Mean Field Game systems because we think that they are very important from the analytical point of view, and we can always characterize their solution explicitly. This can give us some intuitions, help us to learn the properties of the system, its inherent properties and things like that. And moreover, we can look at LQG system as the building blocks of a stochastic system. So we can use them to approximate nonlinear and in some cases interactable systems. Our work is based on this work here. So this work investigates entropy-regularized LQG systems for just a single agent system. There are two related works in the literature in the context of mean field games, which use entropy regularization. The first one is in discrete time and discrete state space. So they don't drive the explicit action distributions, and they develop a Q-learning algorithm, which is a model-free reinforcement learning algorithm to compute approximate equilibrium for the system. The second work is closer to ours, but our work distinguishes itself in several aspects in the setup, in the information patterns that we have considered, and also with the results that we have obtained. There is also another line of research in the literature which deals with mean field control problems, or making the less of dynamics, and they deal with dynamic programming principles. So they consider an MDP, Markov decision process, on the space of measures, and develop dynamic programming on the space of measures. So no entropy regularization is used in this series of works to the best of my knowledge. And what they do is to develop a Q-learning algorithm to learn the optimal solutions and also the equilibrium for the system. So for the purpose of this work, first I'm going to review very briefly classical LQG MFG systems, and then I will compare the results that we will obtain in the exploratory case. So assume that we have N agents in K different subpopulations. So each agents in each subpopulation share the same dynamical parameters and cost functional parameters, which are different from those of agents in other subpopulations. All the parameters are shown here. All model parameters are shown here, and this subscript K denotes the type of the agent. So we are in an LQG setup. Each agent follows a linear stochastic dynamics and has a quadratic cost functional, as in here. So the state process is denoted by XIT for agent I at time t. The control action is denoted by UIT, and WIT is the idiosyncratic Brownian motion for agents. The interaction terms are shown in blue. So they are in fact the empirical average of states over or across agents, and the empirical average of control actions across agents. So in the mean field game methodology, the problem is solved in the infinite population limit, where the number of agents goes to infinity. So what we do is to replace the empirical terms, the average terms, with their infinite population limits, as in here. And then once we do this replacement, this becomes a standard stochastic control problem for agent I. We can solve it. So this problem is much simpler to deal with than the finite population case where there are n agents. So in classical LQG MFG system, it is shown that the set of control actions of this form yield a Nash equilibrium for the infinite population system. And if this set of actions are applied to the finite population system, it yields an epsilon Nash equilibrium for the system. So meaning that if one agent unilaterally deviates from the set of these actions, while others are following these actions, it can at most benefit by epsilon, and this epsilon is inversely proportional with a square root n. N is the number of agents. So the higher the number of the agents, the better is this approximation. And these coefficients that were shown in blue, they satisfy Riccati and offset equations as in here. And in fact, they are solutions to this set of mean field consistency equations. So the equilibrium that we have obtained is subject to this set of consistency equations, whose fixed point solution gives us the coefficients in the optimal, in the control action of the agents. And in particular, I want to point out that this offset equation is impacted by the mean field. As you can see, the mean field terms are shown in purple.
Can I ask a question? It was
Sure.
a little bit, I didn't follow fully the, you have several groups, right?
Yes.
Types of agent. So when n goes to infinity, what is happening with this type of agent? The number of types goes to infinity or stay finite?
No, the type of agents remains the same. So we have k types of agents, but
and the proportion of each type does what?
Yeah, we assume that the proportion. So I haven't included an assumption. So we assume that the proportion of agents in each subpopulation converges to a constant.
Okay.
There is, yeah. So we have this empirical distribution of agent types. So agents have discrete types here, and then we have a discrete distribution that the empirical distributions converges to that. But this can be generous to the case where there are a continuum of agents, and in that case we have the distribution. So we don't have k distinct types of agents, a continuum of agents. Okay. And again, we have one empirical distribution for parameter of the system, which we assume that converges to the to a distribution in the infinite population limit when n goes to infinity.
Okay, thanks.
One more question. So what is the psi here? Is it stochastic process or is it
no, it's deterministic. Yeah, it's just a deterministic coefficient here.
Oh, it's a constant. Okay, I see. Mm-hmm.
Yeah. So I didn't specify it here, right? Yeah, good catch. But yeah, that's just the deterministic coefficient.
Okay.
Yeah.
Thank you.
My pleasure. Okay. So now I'm going to present the exploratory LQG MFG system. So as I mentioned, in this case, we extend the notion of actions to distributions, to action distributions. So consider that we have n independent rounds of experiments for agent I. So each round is indexed by j. And at each round, at each time instant, we select an action according to the action distribution that we have here, and then we execute it to the system. We apply it to the system. So we will have a state as a result of this application of this action, which we denoted by xi. So it's the state of agent I at round j at time t. So if we repeat this procedure for all the times in round j, then we will be able to form these increments for agent i's state. And then if we take the average of these state increments over the end rounds of experiments that we have. As the number of rounds goes to infinity, we can show that this, based on the law of large number, this converges to the expected value of the state increments. And here, the superscript phi is to denote that this state is a result of the actions that have been sampled with respect to the distribution phi and applied to the system. Now, if we take the average of actions that we apply to the system, over the n rounds of experiment and take it to the infinity, and we can, again, based on the law of large number, this converges to the expected value of the mean value of the distribution with respect to which we are sampling actions. And the mean value of distribution is shown by this notation here, mu it. We can, for every term in the objective function, this can be done. So every term in the objective function, when averaged over the n rounds and taken n to infinity, converges to the expected value of the integral of that term with respect to the distribution that we are using. So from this exposition, we can infer that this is the expiratory dynamics for agent I. So as you can see here, first of all distributions phi here are denoted by superscript n because we are in the finite population system. And the actions, the control action in the dynamics is replaced with the mean value of the distribution that we have used. So this mu int is the mean value of the distribution that we have used to sample actions. And we also see that the average of the mean values of the action distribution of agents over population appears in this expiratory dynamics. And similarly, we have the state average. So intuitively, this dynamics describes the average behavior of agent I when actions are sampled from distribution phi I and applied to the system of the agent. And this is different from the mean field of actions, which models the mass behavior of the agents. Okay. Now, in the objective function, so we have other terms that we had previously, as I shown in the classical case, but we have this integral with respect to the distribution now. Moreover, we add Shannon's entropy as in here. So this entropy term is included in the objective function with this coefficient, which we call it trade-off rate. It determines how much expiration we want to permit in the system. The higher lambda is, the higher expiration we will have in the system. And the last term is just to for the constraint that we have. So the distribution of each agent should integrate to 1. So this term is included to make sure that the distribution integrates to 1 in fact. So far I formulated the expiratory LQG Mean Field Game systems. Now I want to show that how we can solve this problem. So the approach is the same as in the classical case. We move to the infinite population when the number of agents goes to infinity. So there, the processes are replaced with their infinite population version, and which are shown here. So in the infinite population case, we denote the action distribution of agent I by phi I, and this is its mean value. To solve this problem, we use a variational analysis. And for this variational analysis, what we do is that we perturb the action distribution in this way, and then we investigate how this perturbation propagates throughout the system. How does it affect the state of agent I? How does it affect the mean field term? And then using the perturbed values of processes, we obtain the perturbed objective functional, and then we can compute the Gatto derivative of the objective functional as the difference of the perturbed objective minus the original objective function over the perturbation parameter when this perturbation parameter goes to 0. We have some technical conditions which are mainly to guarantee convexity of the problem, and subject to those assumptions, this expression is 0 if and only if phi is the optimal action distribution. So if we set this expression to 0, we obtain the optimal action distribution as in here. So interestingly, this optimal action distribution is Gaussian, and its mean value, which is expressed here, is coincides with the optimal action in the classical case. So the optimal action for agent I in the classical LQG MFG systems. This pi and s, the coefficients in the control action, they satisfy offset and Riccati equations, and they are solutions, the fixed point solutions to the same set of mean field consistency equation as in the classical case. So I will give some more interpretations and intuitions about this in the next couple of minutes. So first of all, as I mentioned, this distribution is Gaussian and its mean value is stochastic. So in general, we have a stochastic action distribution, and this mean value is given by the sample path of agent I's state. And this, as I mentioned, this mean value coincides with the optimal control action in the classical case for agent I. Now, if we look at this distribution, we see that the mean value, it's not impacted by this lambda, which is the trade-off weight. So the weight of the entropy term in the objective function, and to be more precise here, I should put lambda k because we consider different weights for agents in different subpopulations. And if we look at the covariance, we see that the covariance of this multivariate Gaussian distribution is directly impacted by this trade-off weight. So it means that if the trade-off weight in the objective function is larger, the covariance is larger, so it means more exploration. So we can interpret that exploitation is reflected in the mean of this Gaussian distribution, and exploration is reflected in the covariance of the Gaussian distribution. This can be viewed as a refinement of epsilon greedy policy. So epsilon greedy policy is a common approach to balance exploration versus exploitation in reinforcement learning, especially in the multi-armed bandit problems. So in this approach, so we first set the value of epsilon. So a random number is generated. If this number is smaller than epsilon, then an action is chosen randomly. So this means exploration. If R is greater than epsilon, then we choose the current best action, which means that we use current knowledge to optimize to solve our optimization problem. So this can be interpreted as exploitation. So we select the current best arm, and by that I mean the best action that has led to the current best payoff with a probability of 1 minus epsilon, and otherwise we select an arm at random with probability epsilon. So this gives a Bernoulli distribution for executing action, and the Gaussian distribution that we obtain can be considered as a refinement of this approach. Again, if we consider the distribution that we have obtained, so if we sample actions with respect to this distribution and we apply them to the original system that we had, to the classical system that we had. So this in fact provides a randomization around the optimal control action of the system. And this distribution, again, I want to emphasize that it's not deterministic. So for our case, in fact, it is stochastic. Now, I want to find the mean field distribution for this exploratory system. So we know that the law of state and the law of control actions gives us the state mean field and the control mean field in the infinite population limit. So in the exploratory case, if we obtain the law of state or the state mean field distribution, it is Gaussian with the mean value x bar, and this x bar is the average of agents state when the number of agents goes to infinity, if it exists. And since we have only minor agents here, this x bar is deterministic. So the mean field distribution is deterministic in this case. Now, for the control mean field, so as we saw in the exploratory version of the problem, the mean value of the action distribution appears in the dynamics. So the control mean field distribution in this case is specified by the law of this mean value. And it is Gaussian again with this mean value. Since x bar is deterministic, mu bar is also deterministic. So both the mean field and the state mean fields are deterministic. And it is interesting to see that both of exploratory and classical LQG MFG systems share the same state and control mean field distributions. But these are different, and especially the control mean field distribution is different from this distribution that a single agent is using to randomize its actions in an optimal way. So this can be shown mathematically. So given the same initial state distribution, the state and the control mean field distributions for the classical and exploratory LQG MFG systems are identical in the infinite population limit. Another interesting aspect when we compare the classical and exploratory systems is that there exists a solution to the exploratory LQG MFG system if and only if there exists a solution to the classical system. So there is this existence equivalence between the solutions of the two systems. Moreover, we can compute the cost of expiration. So the cost of expiration, we define it as the difference in the original objective function of the agent when optimal action distributions are applied and when the original optimal actions in the classical case are applied. So given the same initial state for a generic agent, in both the classical and exploratory cases, the cost of expiration in the infinite population limit turns out to be directly proportional to the trade-off weight. So, and this completely makes sense. So if we give a higher weight to the entropy-regularization term in the cost functional, we have a higher expiration and higher cost of expiration. And this row here is the discount factor. So it is inversely proportional to the discount factor in the objective function. We can also show that when no expiration is involved, so in the classical, like in the classical case, the distribution that we have obtained reduces to the direct delta function. And the value functions, moreover, when the expiration, we don't have any expiration mathematically, when the weight of entropy-regularization term goes to 0 in the objective function, we can show that the magnitude of the difference between the value function in the classical case and in the exploratory case goes to 0. Okay, so while I am discussing the infinite population case, I would like to discuss a little bit about an extension to other entropy terms. So far, I just included Shannon's entropy term, but the results and the distribution that we have obtained, they can be extended to the case where we consider other types of entropy. So, for example, if we consider relative entropy, as in here in the objective function, the optimal expiratory action for agent I that we obtain has this form. So if you look at this form, this second term is exactly the same as what we had for the Shannon entropy. And this is the prior which we have in the relative entropy. So it is like the optimal action distribution is distorted by this prior once we consider relative entropy in the objective function. Okay, so so far I discussed the expiratory LQG MFG system in the infinite population limit. Now I want to make a connection between the infinite and finite population systems for the expiratory system. So assuming that all agents except agent I are following the optimal action distributions that we obtain, and agent I is following is using an arbitrary action distribution, we can show that the expected value of the distance between the finite population state and the infinite population state squared is of order 1/n. Moreover, we can show that the magnitude of the difference between the finite population objective function for agent I and its infinite population objective function is of order 1/n. So this is again with the assumption that all other agents are using the optimal action distributions that we have obtained. So we can use these two properties to show the epsilon Nash property for the expiratory system. So the set of action and distributions that we have obtained gives an epsilon Nash equilibrium for the expiratory system. More precisely, and so if an agent unilaterally deviates from this set of strategies, it can at most benefit by epsilon. And again, in this case, epsilon is inversely proportional with square root n. So the higher the number of, the larger the number of agents, the better is this approximation. Now I'm going to discuss some potential applications of the framework that I presented in this talk. So there are two potential applications listed here. So first is that we can use expiratory LQG Mean Field game systems to approximate nonlinear MFG systems which are not explicitly solvable in general. So this permits to explore the states of nonlinear system which are not captured by classical LQG MFG approximations. And since we have this expiration, we have an improved expiration, so it is expected to improve the performance of such approximations as well. Moreover, the Gaussian distribution that we have obtained here can be used as a policy approximation in model-based reinforcement learning in LQG Mean Field Game systems for learning either the dynamical parameters of the system or for learning the value function directly. So in fact, in this work here in this reference, this has been done for a single agent mean variance problem. So they have used the entropy-regularized LQG system, not in a mean field game setup, but they were able to learn the value function of the agent using this action policy. I want to spend a little bit more time on the second application and to shed some more light on it. So when I'm talking about model-based reinforcement learning, by model, I mean whatever an agent can use to predict how the environment will respond to its actions. And given a state and action, a model produces a prediction of next state and reward. So we can use a preliminary learning algorithm which uses the setup introduced in this presentation in the context of optimal execution problems in electronic markets. So if we consider a market where there are n high frequency traders, and here we look at their trading dynamics. So we have different state processes. So for example, the inventory for agent I, its inventory is traded at rate mu I. So if mu I is positive, it is buying it. If it's negative, it is selling. And when agents make trades in the market, they have both permanent and temporary impacts on the price process. So the permanent impact is modeled by the mid price, the middle price between the best bid and ask in the market. And we model it in this form. So it is impacted by the average trading rate of high frequency traders in the market. So this puts a pressure on the price. So if depending on whether it is positive or negative, it can increase or decrease the price. And this lambda here is the strength of the permanent price impact. And this sigma is the volatility of the market, and W is a Brownian motion that can model noise traders. Moreover, we have a temporary impact on the price, which is modeled in execution price, which is the price at which the agent makes a trade. And it is, in fact, the mid price, which is temporarily impacted by the trading rate of agent I. And this is the strength of temporary price impact. And then finally, we have the cash process whose increments are given by the negative of the price execution, the execution price times the increment of the inventory. So if we consider, for example, a liquidation problem, assuming that agent I wants to liquidate by the end of the trading horizon, this will be the objective function. Where it has an inventory penalty term. So this phi is the urgency parameter. If it's very large, then the agent wants to liquidate very fast. And if it is smaller, or in the extreme case, if it is zero, the agent doesn't care holding the inventory as long as it liquidates all at the end of trading horizon. And this is a minimization problem. So the cash process appears with negative sign. So the agent wants to maximize evidently its final bills. And this is the value of its terminal execution. So in this context, it makes sense that assume that agents don't know the temporary and permanent and temporary price impacts and the volatility, but they know their the parameters in their objective function. So then a model-based learning algorithm can be used to estimate the parameters of the system. So, and this has 4 main steps: initialization, model learning, planning, and acting. So in the initialization, we run the base policy. So this base policy is the action distribution that we obtain. But when, since we are just at the first step, the parameters are chosen randomly or arbitrarily. Then we run this base policy, we sample actions with respect to this policy, execute them, and we have a set of data with respect to which we can estimate the model parameters. For example, we can use a maximum likelihood algorithm, and then we solve the fixed point solution to the set of mean field consistency equations. So while when we have these updated parameters, then we can go ahead and plan. So we can update the action policy that we have using the updated values of the parameters, and also the updated value of the states at each iteration. Then the next step is acting, which is sampling actions with respect to the updated distribution, executing them, and adding the resulting data set. So if we repeat planning and acting n times, then we can go back to model learning to learn the parameters of the system again, and we can continue until we get a convergence. So this was just to give you an idea of how this framework can be used in learning algorithms. This is of course a preliminary learning algorithm, and it resembles very much to the parameter identification in the context of stochastic adaptive control. So I will finish my talk with some concluding remarks. So what I showed was that the best distribution to balance expiration versus exploitation for LQG MFG systems in the in-field population limit is Gaussian. And the mean value of this action distribution interestingly coincides with the classical optimal control action for a representative agent, and this result is consistent with the one for the single agent case in this reference. And when we are able to retrieve the classical solutions when we take the expiration to 0 by taking the trade-off weight in the trade-off weight of the entropy regularization term in the objective function to 0. And this in general can be viewed as a refinement of epsilon greedy policy. So if you are interested to see the full paper, it will appear soon in Automatica, and in the meantime, it is available on arXiv as well. So thank you very much for your attention, and I would be happy to answer questions if there are any.